Welcome to the RC Aero Design Build channel. My name is Tom and I am a radio control airplane hobbyist with an interest in scratch-built model airplanes. The purpose of this channel is to provide design and construction content that will hopefully be useful to anyone interested in designing and building their own model airplane. I'm a subscriber to flow5, which is a next generation application created by the developer of STL5. The user enters the geometry of an airplane as well as an airfoil, and then flow5 can be used to analyze the performance and stability characteristics of the model. But it can also import STL mesh representations of airplanes and analyze them. This is my second video for the channel, and in this video I'll demonstrate how to import an STL mesh, pre-process it, and then perform an analysis. So here's what we're going to need. Firstly, we need an STL mesh that has been exported from a CAD or airplane design tool. We then need some dimensional characteristics of the reference component, and in flow5 we're interested in the true span-wise length of the main wing sections as well as the root and tip chord and dihedral of each wing section. If we're interested in analyzing the stability, we also need the mass of the model. The model that you're watching is the STL mesh that we created in video number 1 using OpenVSP. I'll open up VSP again to examine the model characteristics in order to get the information we're missing. So here we are back in OpenVSP. I'm going to open the demo model that we created in video number 1, and I'll open that. And there's the model. One thing I should point out is in the previous video I suggested that we cut or remove the hub or propeller spinner. However, it does contribute to reducing the drag of the model, and so I suggest you import it again, including the hub. So we're going to take a look at the modified wing, and this wing here is a fairly simple wing. There's basically one main section and it's duplicated. That wing section has a root chord, it has a tip chord, and we can get the true length of this section. And we can also check down in this location to see if there's any dihedral, and there isn't any. So it's pretty simple. Some wings, however, could be a lot more sophisticated, of course, and have multiple dihedrals. It could have wingtips. These wing sections could be swept back, but this one's fairly straightforward. So we're going to look at the plan view. So in this area here, if there's more than one section, we could go to the first section, which would start at this location, and then we could continue to tab outward and pick up every section. Since there's only one section, we'll record the span, which is 21 feet. That's the half span. The root chord at this location is 4.57134 feet. The tip chord is 3.047, and we already confirmed that there is 0 dihedral. So that's all we need. So we'll now open up flow5. I've opened flow5 from a closed state. When it's first open, this is the main page that you see. You can see that this is a beta version 18. I've already created a file. It's called video number 2 demo STL import. And once you open your first file, you get the full flow5 view with the user interface. So we need to select the plane design view, and we need to go to plane import. We're going to import from an STL file, and this import window pops up. The first thing you want to do is indicate the units of measure, and we're going to use meters. It's the largest available unit, and that's to make the resolution of the model as high as possible. We'll be able to scale it back later, and I'll indicate how that's done. So we go to import the file, and there's the STL file that was created in the previous video. We'll open that. It's quite quick. We'll close that, and there's the model. I can apply the surfaces and maybe give it a little bit of color. I don't like that, so give it a bit of color. There are three tabs we're going to work through. First is Metadata, the next is Transformations, and then finally the mesh and trailing edge, where we're going to review this mesh. Let's go back to Metadata, and we'll just call it a Cessna STL plane. You can put in a description of the plane if you want. This is where you would put in the reference area. In our case, we'll use the wing, so we'll put in the reference area, the reference chord, and the reference span. However, at this point, we don't know what that is. I'm going to demonstrate to you how to use flow5 to do that calculation. It's pretty simple, and then we'll come back in and insert that. This tab is Transformations, and there's really two areas. There's rotating and translating the actual model, and the other is scaling the size of the model. So the one good thing about OpenVSP, it uses the same conventions for locating the airplane in the XYZ three-dimensional grid. In this view, you can see that the x-axis, which is the streamwise direction of the flow over the aircraft, goes through the center of the vehicle, and positive is front to back. The origin, and this can be changed, but the origin of the three axes is located at the nose of the airplane for this model, which we'll leave, and the y-axis is from left to right, and right being positive. If I rotate the airplane, you'll see that the z-axis is vertical and it's positive going up. It's important that you rotate and translate the airplane before you scale it, and I'll give you an example why. If we look at this plane, it currently has a width of 42,000 millimeters. That's basically from this location to this location. If we were to translate this around the z-axis by, let's say, 45 degrees, you can see that width has now changed from 42,000 to about 32,000. And the reason is it's measuring from this point to this point laterally on the page. I'm going to change that back, and you'll see that it will rotate back, and we now have the width of the airplane, which we're going to use as the projected span. Now we're going to scale the airplane, and the width here is 42,427 millimeters. We happen to know that the airplane is 42 feet wide, so if you take 42 times 304.8 millimeters per foot, that is, it should be 12,801.6. So if we divide that by 42,427, we need to reduce this to 0.3017 of its current size. So 0.3017, we hit the scale button, and now you can see that the width is 12,800 millimeters, which is the value that we want. So now we have the airplane transformed and scaled to the way we want it. We'll now go back to the metadata and we'll calculate the reference area and dimensions that we need, and we'll insert those prior to going to the final stage of checking the mesh. So we're going to save the model, and we're now going to define a new airplane, and this is going to be a standard flow5 XFL file format plane, and we're going to go and edit a wing, and we're going to use the dimensions that we recorded before, and I'll insert those in the top right hand corner. But the root chord is 1,393 millimeters, and the tip chord is 928.7 millimeters. The dihedral is 0, and the half span length is 6,400. Now see here that the wing area is 14.86 meters squared. The wingspan is 12,802, and the mean aerodynamic chord is 1,176. So that information will input into the STL metadata. I'm back in flow5, and you can see that I've entered in the reference area, the MAC, and the reference span. So we need to save this before we start getting into processing the mesh and the trailing edge. So we'll save that. It kicks us back out. We're going to go back in and edit, and the transformations are done, the metadata is in, so now we're going to process the mesh. So what we're doing here is we need to identify two things in order that flow5 can do an analysis. The first is that all of these triangles that you see on the airplane are connected to one another, and there are no sides of a triangle that aren't connected. The second thing that we want to do is we need to identify what the trailing edge is for this airplane. Flow5 doesn't know, but we will flag all the triangles on the trailing edge of every lifting surface. So that'll be all the triangles on the trailing edge of the wing, the horizontal stabilizer, and the vertical stabilizer. Now, in order to do that, we need to turn off all the surfaces on the airplane so we can actually see these triangles. So we've done that, and the first thing we want to do is we want to connect all the panels together. And down in this window here, it's going to display the status of all these commands. So in this case, we've connected the panels. Now we're going to check for any free edges, and there aren't any free edges. So the next thing we want to do is try to identify all these trailing edge triangles, top and bottom. So there is a technique here for guessing what those are, and that is we start with maybe a 10-degree angle, and we'll guess, and you can see all of a sudden we've picked up some triangles on the trailing edge. So if you read the documentation, it'll explain in detail exactly what we're doing here, and there's a link here that'll take you to that documentation. But if we were to look at this airplane and zoom in, we can see we've picked up the triangles on the, or some of the triangles anyway, on the main wing, but we haven't picked up any on the horizontal stabilizer or the vertical stabilizer. So we progressively keep adding these in until we get to the point where we've captured all those triangles. And we don't want to go too far, because if we we'll get to a point where we start picking up triangles that are in locations other than on a trailing edge of a lifting surface. So you can see that this increment from 20 to 25 degrees didn't add any more trailing edge panels. So we're simply going to connect the panels again. We're going to check for free edges. There are none. And we're going to check the trailing edge. And there's no trailing edge error. So we've satisfied the requirement for identifying all these trailing edge connected triangles. Let's have a look at the vertical stabilizer, and you can see that we've picked up all the triangles on the trailing edge. And if I rotate it and bring it back up here for you to look at, you can see that both sides have been picked up. So we're going to save this, and now we're ready to do an analysis. So here you can see that I've performed two analyses of the STL plane. Both of them are at 35 meters per second, which is about 78 miles an hour, which is just safely above the stall speed. The first one, you can see the drag is significantly underestimated, and as a result the lift-drag ratio is quite high. It's showing an estimate of about 93, which we know is unrealistic. Now if I look at the data points of this analysis, we can see the alpha ranges from -4 to 10 degrees angle of attack. We've got the coefficient of lift and the total coefficient of drag, which is the sum of the viscous and the induced drag. And you can see that there is no data at all for the viscous drag. And that's because flow5, when analyzing an STL plane, cannot see any information with respect to the airfoil or the fuselage, so those calculations cannot be completed. So if we get out of this and we look at this second analysis, we can see that there has been some extra drag added, and we'll edit this and I'll just show you how that's done. There basically are two ways of adding extra drag. One is simply putting in a fixed drag coefficient with a reference area, and the other is to add a parabolic shaped drag. And with these splines you can estimate the minimum drag that will be added plus the shape of the curve as the coefficient of lift changes. So the net result of that is, if we look at the polar data points, you can see that now we have a viscous drag value that's been added that is directly related to the parabolic AVL drag that we selected. The T1 analysis are very fast and give us a realistic estimate of the coefficients for the airplane. The developer, however, recommends that for the best precision we should be using a type 6 analysis, and the wake should be a vortex particle wake with the number of iterations set to 35, and we should also include an estimate of the additional drag. I'm not going to run one of these because the analysis takes quite a bit of time and processing power for the computer. So my recommendation is you start off with T1 analysis to do preliminary predictions of the coefficients, and then once you've made all the adjustments you need for your model, that you then run T6. And finally, before we finish the video, I highly recommend that you go to the online documentation and I'll provide links for you below. And the two subjects that we should be looking at are the external STL mesh, and it'll give you a much more detailed explanation of how to create and process that mesh than what I've covered in the video. And the other subject that you should look at is the vortex particle weight. So that's it for now. See you in the next video.